Look at this metallic cantilever beam oscillating under a heavy load. Real-world physics are continuous, flowing seamlessly through space and time. But to analyze this mathematically using a computer, that flowing reality fractures into a rigidly defined geometric wireframe mesh. A solid physical object possesses an infinite number of discrete points, what engineers call degrees of freedom. Computers, no matter how powerful, cannot calculate infinity. To build functional finite element method software, we need a reliable translator. We need a way to convert the infinite, continuous physics of the real world into finite, solvable equations. This transition relies on variational methods, specifically Hamilton's principle, which reformulates the motion of a system as a search for a specific optimal energy path. We are going to bypass the dense, pure mathematical proofs behind this principle. Instead, we are looking strictly at its pragmatic utility for finite element analysis. While advanced abstract calculus demands rigorous derivations from first principles, our requirement is strictly to build functional, predictive structural models. We will apply this methodology directly to the practical structural analysis of beams, establishing a familiar engineering baseline before scaling up to more complex geometries. By learning how physical systems naturally minimize what physicists call their action, we bypass the need to solve complex vector mechanics. We directly acquire the exact computational tools required for finite element software to analyze structural integrity. Traditional Newtonian mechanics requires tracking individual microscopic force vectors interacting across a structure. Variational mechanics discards the force vectors entirely and instead tracks the total energy of the system. The primary metric we use to track this systemic energy is called the Lagrangian. The Lagrangian is built from two opposing physical states. Kinetic energy represents the active movement of the system, while potential, or strain energy, represents the internal stiffness resisting that movement. The Lagrangian, L, is the difference between kinetic energy, T, and potential energy, V. As this beam flexes, it trades energy. Snapping through the center, kinetic energy peaks. At maximum deflection, strain energy peaks. Plotting the running mathematical difference between these states over time calculates the system's total action. The Lagrangian encapsulates the entire physical state of the structure at any given millisecond. It does this without plotting a single directional force arrow. Computing a single scalar energy gradient is highly efficient. It requires a fraction of the processing power needed to balance thousands of microscopic intersecting force vectors across complex geometry. This concept of accumulated action forms the mathematical basis of Hamilton's principle. This integral equation determines exactly how a system will behave as it moves from one state to another. The boundaries of the integral define a specific window of observation, with T1 as the starting state of the structure and T2 as the final state. To evaluate this integral, we use the variation operator, denoted by the delta symbol. It functions as a mathematical testing mechanism. It tests imaginary alternative geometries, virtual paths that the structure could theoretically adopt between point A and point B. These virtual paths represent physically impossible scenarios where the structural system moves erratically or simply wastes mechanical energy. They stand in contrast to the single, efficient true path. Hamilton's principle dictates a strict physical law. The true, real-world path a structure takes is the exact path where the variation of the action integral equals absolute zero. This zero state is known as a stationary point. It proves the system has found the path of least resistance, minimizing its overall energy expenditure. Because physical reality naturally optimizes for minimal energy, Hamilton's principle gives us a predictive mathematical rule. We can exploit this rule to determine exactly how an unknown structural geometry will deform when a load is applied. For a simple laboratory beam, a single continuous integral works, but for a complex engine component with irregular geometry, there is no single, smooth function that can describe the displacement of the entire part. This is exactly where the specific mechanics of the finite element method must be integrated with Hamilton's principle. This curve shows the continuous displacement field of an object. It's a smooth function, labeled u of x, t. We solve this through discretization. The curve dissolves, shattered into isolated data points called nodes, labeled d sub I of t. Between these nodes, we approximate physical space using shape functions, restoring mathematically solvable continuity across the discrete framework. Next, we inject our newly created discrete nodal variables directly into the kinetic and potential energy terms of Hamilton's integral. We then apply the variation operator specifically to these discrete nodes. Instead of testing virtual displacements across an infinite mathematical plane, we test them only at these fixed coordinate points. By combining the variation operator with discrete nodes, we isolate the specific equations of motion for a single finite element. This creates a functional, scalable building block for the software. By applying the variation to our discrete nodes, the integral is evaluated across each local shape function. This process transforms the calculus into a system of algebraic equations, where the energy terms are weighted by the specific geometry of the element. This system of equations is expressed as a matrix relationship. The spatial distribution of mass and the internal resistance of the material are organized into distinct grids of values, resulting in the classic structural dynamics equation. Every piece of this equation maps back to the Lagrangian. The mass matrix M is derived directly from the kinetic energy term, and the stiffness matrix K is derived directly from the potential strain energy term. By calculating these matrices for a single element, a computer can mathematically stitch thousands of them together to accurately represent the global behavior of the entire continuous beam. There are boundaries to this approach. If you're handling highly advanced, highly nonlinear, specialized physics problems, this simplified, pragmatic foundation may expose some gaps requiring further mathematical rigor. However, for standard finite element analysis and for the curriculum covered in our upcoming engineering models, this foundation is entirely robust. Translating abstract variational physics into discrete mass and stiffness matrices takes the concept of energy minimization out of the textbook. It equips engineers with the exact operational tools required to model and solve complex structural realities in software.